We're going to look at graphing complex numbers. And remember, complex numbers are of the form a plus bi, where a is the real part and b is the imaginary part. Well, we already know how to graph real numbers. We graph real numbers on the real number line. So if that were 0, and then we say 1, 2, 3, 4, 5, we could go negative, -1, -2, -3, -4, -5. So this is the real number line. However, there is another number line, another axis, and it is the imaginary axis. It's perpendicular to the real axis, and it goes through 0, 0. And this one can also have 1, 2, 3, 4, 5, and -1, -2, -3, -4, -5. So when we graph complex numbers, what we need to do is graph the real part and the imaginary part. It's sort of like coordinates. You can think of it as using the XY plane. I went ahead and drew my real number axis and then my imaginary number axis as well. And we're going to graph a few complex numbers. First complex number we're going to look at is 2 plus 3i. What you need to do is identify the real component and the imaginary component. The real component is 2 and the imaginary component is 3. So what you need to do to graph it is move 2 over on the real number line and up 3 on the imaginary number line. So there's our point. We have the point 2 plus 3i graphed. Cool. That was it. Let's look at another one. Let's graph -4 minus 5i. So the real component is the -4 and the imaginary component is the -5. So when we graph it, we're going to go -4 on our real number line and -5 on our imaginary number line. So the point right about there would be the point -4, -5i. Hi, let's look at -2i. The real component of this number is 0. There isn't a real component. The imaginary component is -2. So you need to move down -2 on the imaginary axis, and that's it. This is a strictly imaginary number, so it lives on the imaginary number line. So a counterexample of that would be if we were to graph the number 4. The imaginary component of this number is 0, and so it only has a real component. We graph the real component of 4. This is a real number. It lives on the real number line. So let's do another couple of complex numbers. Let's look at the complex number -1 plus 7i. See if you can identify the real component and the imaginary component. Remember, the real component is graphed on the real line, and the imaginary component is on the imaginary axis. So the point -1, 7 would be way up towards the top of my little graph. And let's try one more. Let's look at 3 minus I. So what's the imaginary component of this one? Just like if we had minus x, minus I is the same as saying -1i. So the real part is 3 and the imaginary part is -1. When we graph this, we go over 3 and down 1, and we have the graph of 3, -1, that complex number. We're going to be looking at another couple of things with our complex numbers. We're going to want to look at the magnitude of complex numbers. So I'm going to move to a new slide since I'm running out of space, and we're going to start looking at what magnitude means. You have already talked about magnitudes with vectors, and magnitudes with complex numbers is very, very similar. One of the complex numbers we graphed on the last screen was 2 plus 3i. When we graphed 2 plus 3i, we went over 2 on the real number axis, and we went up 3 on the imaginary number axis. Now, if we wanted to find the magnitude of 2 plus 3i, we would be looking for its distance from the origin. So if we look at what we have right here, we really have a right triangle. And all we're doing when we find the magnitude is we're finding the distance from the origin to the imaginary point the complex point, 2 plus 3i. When you want to find the magnitude of a complex number, you would use the absolute value bars. That says, hey, find the magnitude. So let's think about our distance formula. Our distance formula says what we need to do is find the distance traveled in the horizontal direction, the distance traveled in the vertical direction, and take the square root of those squares. So according to the distance formula, I'm going to find the square root of 2 squared plus 3 squared. Okay, so again, using our distance formula, simplify a little bit. That's going to be the square root of 4 plus 9, which is the square root of 13. Now that we know how to simplify with square roots, we can think, are there any perfect squares that go into 13? No, so that's it. The magnitude of that complex number is the square root of 13. Let's look at another one while I still have a wee little bit of space on this page. Let's look at the magnitude of another graph we did. We did negative 4 minus 5i. This one has negatives in it. Let's see how that affects it. When we graphed this, we did negative 4 on the real number axis, and we did negative 5 in the imaginary axis. If we want to find its magnitude, we want to find its distance from 0. So you can make yourself a nice little right triangle, and we'll notice that the change in the x direction was 4, the change in the y direction was 5. So when we put that into our distance formula, we're going to have the square root of 4 squared plus 5 squared. Really, if I were to just put that negative 4 and negative 5, since I went in those directions, that doesn't change anything because negative numbers squared are positive. So let's simplify this a little bit. We're going to end up with the square root of 16 plus 25, which is the square root of 41. Are there any perfect squares that go into 41? Unfortunately not. So that's the end. That's our magnitude for that point. I should be able to see this pattern here. What we're doing to find the magnitude is we're taking the square root of the squares of the real part plus the square of the imaginary component. So we wouldn't even need to graph them to find the magnitude. When we originally graphed some imaginary and complex numbers on the first slides, let's go ahead and find the magnitude of some of those. One of the numbers we graphed was negative 2i. It was a strictly imaginary number, and it lived on the imaginary axis. Just because it lives on the imaginary axis doesn't mean we can't find the magnitude of this. So let's go ahead and find the magnitude. Now, just to remind you, I know I said we weren't going to graph, but the graph was negative 2i down from the origin. No triangle is created, so if we went straight down, the distance we travel is just right there. It ends up being just 2. However, let's use our formula to write out what the magnitude would be. It's the square of the real component plus the square of the imaginary component, and take the square root of that. Well, the real component is nothing, it's 0, and the imaginary component is negative 2. So negative 2 squared is 4, so we end up with the square root of 4, which is 2. So the magnitude of that imaginary number is 2. It's 2 away from the origin. Another number that we looked at on that other slide was negative 1 plus 7i. So if we want to find the magnitude of this number, we need to find the distance from 0. That means we need to find the square of the real component, the square of the imaginary component, and take the square root of that. Negative 1 squared is positive 1. 7 squared is 49. So we end up with the square root of 50. Now, since we can simplify square roots, we think, are there any perfect squares that go into 50? There actually are. It's 25. So this is the square root of 2 times 25. Square root of 25 is 5. So the magnitude of this complex number is this 5 times the square root of 2. There were two other numbers that we graphed initially, so I want to find the magnitude of those numbers as well, and then that'll be it. We graphed 3 minus I. Now remember, that meant the imaginary component was -1, so our point was over 3 down 1. If we want to find the magnitude, or the distance from 0, it looks like we are going to have the square root of 3 squared plus -1 squared. This is going to be the square root of 9 plus 1, which is the square root of 10. Are there any perfect squares that go into 10? Nope. So we're done. The square root of 10 is the magnitude of the complex number 3 minus I. And then the last number we looked at was 4. We want to find the magnitude, or the distance from the origin, for the number 4. Well, that was just on the real number line. I'm going to graph it in blue up there. That was just 4 over on the real number line. So if we went 4 over on the real number line from the origin, we just traveled 4. This is similar to the solely imaginary number. Let's go ahead and use our formula anyways. The square root, just so we can prove it, is the real component squared plus the imaginary component squared. This ends up getting us the square root of 16, which is 4. So the magnitude of the real number 4 is just 4, which makes sense. Its distance from 0 is 4. So this was looking at graphing complex numbers and finding their magnitude. When we graph them, we need to graph the complex, you need to graph the real component on the real number line and the imaginary component along the imaginary number axis, which is perpendicular up and down. You can think about it in terms of at the xy coordinate plane. When you find the magnitude, we need to find the distance, so we use the distance formula.